Welcome back, everybody. I hope you had 15 refreshing minutes where you could think about other things than the lecture and now come back with a fresh mind for a fresh new part on index construction. So you see, as you can see on the picture behind me here, we are very ambitious. We are really going to build something massive to be able to index even if there's, I don't know, potentially petabytes of books. Right? So we are going to look into the secrets of how to do this and how that's even possible. But before we do that, I have two questions that I would like to ask you. That's on the past, on the previous thing, and then another one that is forward-looking. So, here is the first question that I would like to ask you. Okay. Oh yeah, of course it brings me back here. I need to click again. That's okay. Just need 1 more second. And here you go. What is the most accurate definition of a type? Do you remember? We talked about types in the previous weeks. Is it an equivalence class of postings? If two postings have the same document ID, then they appear jointly in the index. Or is it the resulting set of a query expansion used to query the index? Or is it an equivalence class of documents, which induces an equivalence class on tokens as well, called postings? Or is it an equivalence class of tokens, similar semantically, and types then appear as terms associated with posting lists in the standard inverted index? Which is it? Careful, because I'm very, very good at making up stuff that doesn't make sense, but pretends to make sense. So 3 of these answers basically don't make any sense at all, and only one of them does make sense and is the correct answer. So where are we? We have a majority for the last one. And indeed, the last one is correct. Indeed, remember what we did. We grouped words together that kind of belongs together. For example, be, am, are, is, you know, the conjugations of the same verb. We put them in the same equivalence class because we want to index them together so that when we query for one, we get the other as well. So we group them in an equivalence class. This equivalence class is indeed called the type, and the type then will appear in the standard inverted index, but then we call it a term. So term is the word we use for every key in the B+ tree, basically in the standard inverted index, we call them term. Type is the word that we use when we do the pre-processing, right? That we tokenize, we get the tokens, we group them, we get types, and then they become terms. All right, so this is the correct answer. The resulting set of a query expansion, no, because that's not an equivalence class. We saw that in the case of query expansion, it's not symmetric. So you cannot actually group words in packets. It doesn't work. It's just a one-way thing. And an equivalence class of documents, no, that's not what it is, right? We never really grouped documents together, in fact, in the lecture so far, I think. All right, so this was one of, and you didn't fall for the first one. All right. All right, what else do I want to ask here? Let me see. I need to click again, maybe. It was this one. That's a forward-looking question, because if we want to do things at large scales, with building our standard inverted index with petabytes of data, we need to understand a bit of hardware. So I'm asking you to sort the following storage layers from the slowest to the fastest. in terms of latency latency. We are not in Who Wants to Be a Millionaire. I know the question sounds a bit like that, but just sort this for, I don't have any millions to offer. So we do have, if I show you your answers, we do have a majority saying that magnetic tapes are extremely slow. Then that would be hard drives or flash drives, SSDs, then the RAM, the working memory, and then the CPU cache. Of course, you're computer scientists, right? So that was an easy question, but it's good to refresh your memory. All right. Okay. So now I'm going back where we were. Okay. Oh, by the way, no, I'll say during the slides. I have something to add to the Sandex algorithm. That's actually pretty cool. Okay, so far, what have we done? We have looked into the standard inverted index. What is this thing? It's the structure that we built in order to accelerate and make efficient the execution of Boolean queries. Right? Because then you take the terms in the Boolean query, you look them up here with the B+3 and so on, and then you find the posting list, and then you intersect, union, whatever, and then you get the lists of the documents that you return. Okay, so that's a very important structure. And then it's called standard, of course, because we modify it. We tweak it in many different ways. Okay. Now, these terms right there, they are not just organized like that alphabetically so that a human being does binary search. No. We use data structures. So we saw we can use hash tables to organize the terms, or we can use B+3s. So B3s, of course, would work, but B+3s are more efficient with the access to disk. Remember that this is motivated by block access, the B+3s. It means that the leaves of the tree correspond to a block on the disk, so you just read the block in a single read from the disk. Okay. Then we looked into tolerant retrieval, which is, for example, wildcard queries, where we have an asterisk here in order to allow for any characters. We look into spell correction if I make mistakes. And I told you, I repeat it, make all the mistakes you want in this course. Maybe not in the quizzes and at the exam, of course, but all the rest of the course, all the mistakes you want, including these ones. And in that case, we spell check. Okay. Then we looked into the permuterm index. This was the rotation. When you have a word, you arrange the letters of the word nicely on a circle, you add a $, before the start of the word, and then you just rotate the ring, and that gives you all the rotations of the word. And this is how the $, actually moves. Then we looked into k-grams. Here, the $, must be at the beginning and at the end. And then you have this sliding window left to right on the word that gives you all these k-grams. Here, k equals 2. But again, we saw it can be 3, can be 4. Beyond that, of course, theoretically, but makes less sense to implement. Okay. We looked at the edit distance, which is the minimum sequence of modifications we can have, the number of modifications, the minimum one between two words. Right. It's also called the Levenstein distance, by the way. That's you might find it under that name too. An alternate way of looking at the distance between two words is the Jacquard coefficient, which is the size of the intersection renormalized with the union, right? So it's how many in the intersection divided by the total number of k-grams. That's the Jacquard coefficient. 1, it's almost the same word. 0, very, very far away. Then we looked into the Sandex encoding, which is a way of finding a fingerprint that tells you how a word sounds. And as an exercise, I mean, you can think about these things. I told you that Sandex is designed for the English language, exclusively for the English language. Ask yourself, I'm assuming who, okay, let me ask, who is a Swiss German speaker here? Raise your hand in the lecture hall, in the chat, I'm pretty sure a lot of you. Okay.
People. Yeah.
Okay. So Swiss German, it's a very interesting language, by the way. It has a feature that makes it a bit unique. It is that when you have a consonant that is followed by another consonant, when it's pronounced, the consonants merge in some way. Let me give you an example. There's a part of Zurich called Stettbach, right? S-T-E-T-T-B-A-C-H, Stettbach, because I pronounce it slowly, right? Stettbach. But if you actually pronounce it normally, what you will hear is Stettbach. You will not hear the T at all. Why? Because the T gets swallowed by the B and actually becomes a P. Right? I think it's called an Angleichung, the term for that. And that actually changes the Sandex algorithm, because when you see written Stettbach with TTB, you are not going to encode T and B as two sounds. You should actually change that to a P and then encode the P, right? Another example is when I like in Zurich, the Zürich Stadtbrot, right, that you buy in the bakery. But nobody says Stadtbrot, you say Stadtbrot, right, with an actual P. There's the same with the DF, for example. You don't say tf, you say pf. So the D turns into a P when it's in front of an F. And I would be curious to know, I mean, you can ask yourself, some of you might have been aware of that. I know that some of my Swiss German friends were not aware of it. So it's something that you find in when language experts actually describe it, but it's something that it turns out many people do without really realizing it. So again, think about the consequences, for example, on the Sandex algorithm. If you try to do it on Swiss German instead of doing it on English, then that would be a very interesting problem to solve. All right, but enough said. I think you have understood now that I love languages, but let me stop the parenthesis here. All right, so now a few words on hardware. So first, I must make a disclaimer. I'm a database person. It means that I query stuff, I build indices, and I implement query languages efficiently. When you do that, you have to kind of know what's going on the hardware side. Why? Because you need to understand why things are slow and how to make them test slow. So basically, I have this vaguely abstract understanding of what's going on the hardware side. So of course, it's an abstraction level. I'm apps level. I'm not a specialist of hardware. But what I know about hardware is I know mostly how to compare these things, and that this is slow, this is fast, and so on, and what does what, right? So all I need to know is that a CPU is basically computing stuff, and memory is kind of storing stuff. And the disk is also kind of storing stuff, but it's slower than the memory. And I also know that if I plug if I switch off the electricity here, I'm losing that, and here I don't, right? So, you know, this is the kind of level of abstraction that a database person would have. Then you also know that there's the network, because the computers communicate with each other, and the network has a certain speed with which it communicates. But of course, it can also, there can be traffic jams on the network, right? So you see, this is kind of the level at which you understand things. We are not going to the level, for example, of electrotechnique, right? So I'm not looking at the bits that are actually circulating in the registers of the CPU. This is a bit less relevant at our level. But basically, with that abstract knowledge of the hardware, we can actually think about how we build the architecture for building the actual index of the standard inverted index. So this is what we are looking into today, what happens behind the scenes. And this is why I asked you to sort this for, just as a refresher, because this is actually important. These are all the ways that we store stuff. Okay, so back then, thousands of years ago, this was clay tablets, right? But now we have better ways than clay tablets to actually store things. So the general knowledge is, you know, that this is volatile. So what you have in the cache of the CPU, again, if you remove the electricity, it's all gone. The same for the memory. This is non-volatile for the disk and for the tapes as well. Now, some of you might actually be thinking, what is this thing that almost looks like an archaeological artifact, right? Like, do we even still have that in 2022? Well, actually, it turns out we do. Because when you save data on your drives at ETH, you probably have a home directory somewhere. It turns out that this is backed up, and this is actually backed up on tapes. But the way, the reason is that it's actually extremely, so because you might think, okay, a tape is super slow to read, right? Compared to a disk that's faster, memory faster, cache faster. It's super slow to read, but this is the thing. Tapes are extremely cheap. It's extremely cheap and inexpensive. So this is the reason when you want to save data or back it up for the long term, tapes are still here today. So of course, it's not like before that you needed actual people. So now you have these little robots that automatically go and fetch the tapes and so on. But of course, the latency of that is going to be huge, right? Because you need time for the robots to actually go get the tape and then bring it back to you, right? But anyway, these are all these levels of storage. And whenever you actually query data, you actually have to let it flow around. And then you need to select carefully at what level you make the data flow around to get the desired effect, right? So today we're also working under the assumption that we have a von Neumann architecture, right? Maybe there will be more in the future that will get invented, but for now, this is kind of how it works, right? Okay. So, but again, I'm a database person. So when I look at that hardware, I also like to look into three things that actually are relevant for me in order to measure the speed at which I'm going to build my standard inverted index on petabytes of data. I'm looking at three things. I'm looking at the capacity, the throughput, and the latency. Okay, what do I mean with that? The capacity is how much data you can store. So how much can you fit in a hard drive, for example? You can have a hard drive of 1 terabyte, of 10 terabytes, of 20 terabytes. That's your capacity. Let's call it that way. An example also could be a book in which you have 600,000 words. Right? Then you have the throughput. The throughput is how fast can you read it? How many bits per second can you read from that? That would be the transfer speed, the transfer rate from the hard drive, for example. Right? How fast can you transmit the data over, right? So this is in bytes. This is in bytes per second. And for a book, that would be, for example, 1,000 words per minute, if you want to do an analogy with books. And the third one, latency, is when do you start receiving the data? It's the interval between your request of the data and the time at which you start downloading. Now, other people would call latency until the end of the download. I like to only measure between this and the beginning of the download because this is what I'm interested in from a database perspective. So how much do I need to wait until I receive data? Again, in the case of the book, that probably has a latency of 1 minute because you need to stand up and go fetch the book. That's also what I told you about the tapes, that the latency for tapes is very large because you need the little robots to actually go get the tape in the shelves. Right? Okay. So now, what's very important to understand, I'm actually giving you a sneak peek on the big data material that maybe you will take in fall, I don't know. The progress made in these three, capacity, throughput, and latency, is a catastrophe. I'm going to be honest with you. Why? Because capacity has evolved by a factor of like 200 billion, right? And throughput, barely. It's like times 10,000, 20,000, and latency is even worse. That's the progress if I look between the 50s and today. So we had huge storage capacities. We have very dense hard drives and so on and so on. But in relative terms, we barely can read them anymore in relative terms. The speed at which we read the hard drives is a total catastrophe. And the latency in comparison is even worse. And this is actually the limiting factor for all the large-scale systems that we are building, such as building a standard inverted index for millions of books, right? Just to give you that you know the numbers, I mean, again, you're computer scientists, so you're probably familiar with the ranges, but let's just be clear. In the CPU cache, maybe you can have up to a few megabytes. In working memory, 8 gigabytes, maybe 1632 on your laptops. If you're in a data center, maybe you can even have up to 4 terabytes. On your drive, if it's an SSD, maybe a quarter or half a terabyte, all the way to 12 or even 20 terabytes. I think nowadays we even have hard drives of 20 terabytes. And the tapes, you can go even to huge ranges in a tape factory or in a tape warehouse, what you can store in there. The petabytes is, of course, not maybe a single tape, but if you consider the entire building in which you have the tapes and the robots to be the storage unit, right? Then you can store petabytes. All right. Then the latency, you see that here the latency it's very short for the cache, but the more you move here to the cheap ones, the more time it takes, right? Nanoseconds for the memory, milliseconds for the disk. You see, this is because of the moving parts in the case of a mechanical disk, a bit better for flash drives. And here, as I said, the time for the robots to move, you easily need minutes or even hours If you have other people who need tapes, then you even need to queue. All right. So, and the throughput, finally, the speed at which you can read. Maybe a tape is slow, 200 megabytes per second. A disk, roughly, that would be a mechanical disk, maybe half gigabytes per second. Again, you do have new disk models that maybe push that a little bit to higher speeds, right? But the order of magnitude is kind of that, right? Maybe let's remember a gigabytes per second for a disk. The memory is 10 times more, so 10 gigabytes per second. And then the cache, it's 1 terabyte per second. Okay, now you're going to tell me, what's terabytes on a CPU cache? Well, that's just because I divided by second, right? But of course, you don't do it during one entire second. So this is why you would theoretically read a terabyte if you waited for a second, but it's shorter intervals. But you see that in comparison, the throughput here is insanely high, but here insanely low. Oh, wait, okay. Now, why is that? It's because the disk has moving parts. You actually have a head that needs to move there. This is the reason why it needs time. So if you want to fetch just 1 byte on the disk, what's going to happen is that you need to wait until the reading head actually moves and the disk rotates to the right position, and then you can read your byte. But this here is ridiculously short in comparison to the latency. We say that it is latency bound or seek bound, right? It means that most of the time is spent just waiting for the heads to arrive somewhere. That is exactly the reason why we don't even do that. There is no way you just read 1 byte from a hard drive. That's not how it works. Instead, we like to read in blocks because we don't want to have to wait for the reading head all the time. So in particular, we like to have, that should be a big B, 64 kilobytes, for example, at a time. It really depends. I think if you just do on the low level, it's maybe 4 kilobytes. Database people maybe do it at a higher level, multiple blocks at the same time. But anyway, we read not a single byte at a time, but thousands of bytes at the same time. What does it change? Well, now we spend most of the time actually transferring things. And in relative terms, in absolute terms, it's still the same time, but in relative terms, the time spent in actual waiting for the heads to move is very short. We wait for the head to move. Once it's in place, we just let the disk rotate and transfer the disk, right? So this is very important to understand. It's absolutely fundamental to understand that because that motivates parallelism and batch processing. All right, so the data is sent between the disk and the memory in blocks. Let's say, for example, 64 kilobytes, and it's 1 block here, 1 block there, but never 1 byte at a time. All right. You can cache stuff. So when you read something from a disk and you might reuse it, then maybe you can keep it in memory just in case, then you don't need to read it again. Another aspect, I'm throwing a lot of things at you, right? But it's just a brush up, is that in some cases, the problem you have with your program that you're doing is that this is the bottleneck. You're basically heavily reading back and forth from the disk, and you just transfer. Hopefully you do it with blocks so that it's because of the throughput. So it's throughput bound and not latency bound. But you see that here, it means that the CPU is idle. So the CPU is often going to just wait and do nothing because this is where things are slow, right? This is where the bottleneck is. For this reason, what we like to do is to compress stuff. So it means that we store less bits because we optimize it's the Shannon entropy, so information theory. We like a zip file, so we store less. And then what happens is that we need to work on the CPU to decompress. But overall, we are better because we have much less to actually transfer from the disk to the memory. And then the idleness of the CPU becomes used because now we use the CPU to actually decompress. So this is one of the ways to make it faster is to use this decompression. Actually, this is so important that next week, we'll have an entire lecture just on compression, just on how to compress the standard inverted index, which is complementary to what we are doing today about actually building it, right? Okay, any questions so far before we start building our system? No questions. I hope it's not because you're all asleep, right? I hope what I'm saying is still interesting. Okay, so let's look into what is called term IDs. Remember that the terms, it's what we have on the left right now. And the terms are associated with posting this. Now, On the logical level, I already told you once or twice that this thing right here is a posting. A posting looks like a document ID, right? That's document 8 that contains the term ETH. But I told you, no, a posting is not just the document, it's a pair document term. This is actually the pair made of ETH and 8, right? It's just that since everything here is ETH, we don't repeat ETH all over the place, right? But actually there is implicitly ETH everywhere here. It's just once right there. But if I do this logical development, what I end up with is this. This is the actual logical posting. When I have one, I actually mean ETH1, the pair term document, ETH1. This means ETH appears in document 1, right? Here we have ETH appearing in document 2, ETH appearing in document 3. Okay, I did it for all the terms. Right? These are the actual postings, if you express them as a pair of a term and a document. Now, let me rewind. So this is the actual index once we have built it, but before we build it, we actually produced the postings, and I actually did it 2 weeks ago. Let's rewind how we did that. What happened is that here it's all organized by term, right? Grouped by term right there. Before it was grouped by term, it was all shuffled around, right? Because this is just how it was. We had our pairs that we had generated from the collection. Right. And before that, they were not grouped by term like this, but they were grouped by document because this is where they came from, the documents. So the postings were grouped here. That's all document 1 that has 4 words, ETH computer data information. We just don't know in what order and in what occurrence. Here we have document 3 with these terms, document 2 with these terms. All I did here is just shuffle things around. I just shuffle it around, but now it's grouped by document. And then this is the original document. So I just came back in time, right, in the process. Now, you notice this intermediate representation that I have here that has the terms, but you see that here there is compression potential. Why? Because I repeat a lot of things. And you know that when you repeat a lot of things, this is where you can gain some space by compressing. If you have a lot of repetition in a file and you zip it, then the zip file is going to be very small for that reason. So it means, why do we repeat ETH all over the place? Can we not just encode it in some way? Well, we will do that. And in order to see how much we gain from that, I'm going to do little thought experiments. So we have this. Let's assume I have 1 gigabyte of text. This is my input collection, the one that I want to index. We have 100,000 documents that occupy this gigabyte of text. And if I look into these documents and tokenize, I have 100 million tokens. I'm assuming here non-positional tokens, meaning that I dropped the occurrences and the positions. Okay, now let me do some math. Let's take 1 token. Here I'm not considering the types and the post-processing and the lemmatization. It's all orthogonal, right? But let's assume I just picked a token and I'm just making it a term. So let's assume here we have 10 bytes in average. That's reasonable, right? For the size of a term, let's say take 10 bytes, 10 characters. Let's assume here I have 4 bytes, right? So this is 32 bits. That means that I can express 4 billion. I can index 4 billion documents. That's probably enough. Okay, now when you say it's enough, you need to be careful because you probably know what happened to YouTube when they said that 32 bits is enough, and then they had the Gangnam Style video that actually completely crashed their counter. And this is how they had to switch to 64 bits, right? Okay, but here, let's just assume 32 bits and assume this is enough. Then we have 14 bytes in total, 14 bytes times 100 million. This is where it comes from. I said 100 million tokens. Each token occupies 14 bytes when it's converted to a posting. And that gives us 1.4 gigabytes. Right? So we have an original collection of 1 gigabyte, and the postings in the intermediate representation take 1.4 gigabytes. Okay. Now let's assume I have a 16 gigabyte computer and I'm building all in memory. How much do I squeeze? Can I squeeze more than this collection? The answer is yes, it's just a division, right? It turns out that if you do the division, what you can squeeze in memory, all the number of postings that you can squeeze in that way, you can actually squeeze 1 billion, 100 million token, 1.1 billion tokens. And 11 gigabytes of text. That's the original collection, right? So you can basically take a collection that has a size of 11 gigabytes with 1.1 billion tokens. If you have a computer with 16 gigabytes of memory, then you can build all of these postings in memory, the intermediate representation, right? And this is the most memory usage you're gonna have. Of course, when you then build the inverted index, then that's less again, because then you no longer duplicate the terms. But while you are building it, you have these postings, and thus you have a peak at 16 gigabytes. Okay, does it make sense? So this is what I fit. This is what I can actually do, what I can process with my 16 gigabyte laptop. I can process a collection of 11 gigabytes. Okay. But as I said, that's a peak. That's because at some point we were occupying a lot of space because we have duplicates all over the place. What can we do? We can actually replace these terms that are repeated with a code that takes less space. Let's just give them numbers. This is what we call term IDs. I'm going to say, okay, ETH is 1, Zurich is 2, computer is 3. So you see, I'm replacing the term with just a number, T1, T2, T3, and so on. And then, of course, somewhere I'm keeping the mapping between the terms and the term IDs somewhere else, right? But you see that this here is going to take less space than this. That's the reason we do that. There is a name actually for that in databases. That's called the dictionary encoding. When you do that sort of things, right? You try to remove duplicates by replacing words or values with a code. We check the time. Yeah, still have time. Okay, so in order to have this, where I replace the term with its number, its term ID, I need to keep a separate mapping to know the link between the two that says, okay, ETH is 1, Zurich is 2, computer is 3, and so on. So I need to keep that separate, but the size of that is pretty reasonable, right? Because again, that's only once for each term. Okay, but now let's do our little computation again that we did earlier, right? So back then, we said that this was 10 bytes, but now I compressed this, I squeezed it. So it's no longer 10 bytes, now it's 4. Let's assume that. Let's assume that I have at most 4 billion terms. So I can use 4 bytes for my term ID. Let me assume it's constant size. We'll see how to compress that more, but let's assume it's constant size, always 4 bytes for this, and always 4 bytes for the document ID. Now I need 8 bytes per posting at the peak when it occupies the most space, times the number of tokens. If I had the original number, which was 100 million, is 0.8 gigabyte, right? And now let's try to inflate that to fit the entire laptop of 16 gigabytes, right? How much can I squeeze in there? Well, now I can actually squeeze 2 billion tokens, and I can squeeze an input collection of 20 gigabytes. That's an improvement. It used to be 1.1 here, and it used to be 11. So you see, with exactly the same laptop, very important, I still have my laptop with 16 gigabytes of memory, but now I am able to process in memory almost double that, double what I had. Now I can process 20 gigabytes of text. What's very impressive is that now the collection is even larger than the memory, right? That's actually quite impressive because it's on disk, of course, the collection, not in memory. All right. So is it clear, this mapping to the term IDs? Any questions? Anything unclear? I'm assuming yes. Okay, let's assume yes then. Let's assume yes. Okay. So now that we have this mapping, I'm going to drive you, probably we have how many minutes? 10 minutes left. So I'm going to drive you through a way to build even larger collections. Can you imagine that? Even larger than that. How do we do that? Well, imagine on disk, I can actually fit 20 terabytes of data, right? If I take the largest available commercial disk that I can find, I can squeeze 20 terabytes in there, right? If I didn't care about speed, I could just do everything on disk, right? Why don't I use the disk as memory, right? I can just because we can. So let me just do everything on disk. Maybe it's gonna take, I don't know, 1.5 million years, I don't know, to do that, but let's try. So if we do everything on disk, and we do our little computations. If I have, let's take 12 terabytes of disk, then if I do my division, I can actually index 5.3 terabytes of text. And that's actually, it's so much that I can barely read it. It's 530 billion tokens. That's absolutely gigantic, right? So 5.3 terabytes of text. And then for the index construction, I might use an extra 6.7 terabytes. Okay, so this is what we can squeeze if we didn't care about speed at all, right? So I'm not even doing too much in memory. I'm just writing everything, all the intermediates, posting list, everything on disk. So at the peak of usage, I'm filling the entire disk. This is what we can squeeze. Now, we care about speed because I don't think you want to wait for 1 million years before you get your standard index, right? So we do care about speed. How do we do that? The solution, there's a magic word right there that you can learn by heart. It's called batch processing. Batch processing means that even though the memory is much, much, much smaller than the disk, right? There might be 12 terabytes here, but only 60 gigabytes here. We are still able to build an index on a collection that is as very large on the disk that doesn't fit on memory. But by being smart, I still manage to build my index in the end. And I'm faster than if I had done everything on disk. How does it work? Batch processing. That term actually comes back to the very early days. I was not even born. That's just to tell you how long ago that was. Back then, the computer science department didn't even exist yet. And it was just in the mathematics, electrical engineering departments. There was a room with this supercomputer. And back then, the programs were on punch cards, right? What happened is that the PhD students or the students just brought their punch cards to the office, and they would come back the next day in order to get the results, in order to notice that it actually had bugs and they need to do it all over again. You can imagine the pain that it was back then. But anyway, what happens is that they go to the office, give their punch card, and actually what happens is that they get accumulated the punch cards, right? They just pile up the punch cards, and then they just process them when the next window comes. This is what it's called batch processing, because there's a batch of punch cards, and this batch is going to be processed together. That's called batch processing. And we are going to do exactly the same thing. It means that we are going to index of course, the entire collection. It's going to be gigantic, size of the disk, but we are doing it in batches. First, a little batch, then the next batch, then the next batch, then the next batch. This is how things are going to work. So what we do is that our collection, that's the billion books that we want to index, so the terabytes of data we want to index, we shard the collection. Maybe we can do it on disk. We just need to specify the size of the shards, right? And the size of a shard is in such a way that the shard would fit in memory, right? So maybe I have here, to just keep it simple, 16 gigabytes, 16 gigabytes, 16 gigabytes, right? Although that was a terabyte. This is called sharding, right? And what's going to happen then is that I'm going to process these shards one after the other. First, these documents in the first shard, and then I have enough memory to do that. Then the second shard, then I use my memory to do that, then I'm done, then the third shard. So you see that at any single point in time, I'm only working on a specific shard. Right? Another name is batch. This is my first batch, this is my second batch, this is my third batch. All right. This is why it's called batch processing. This is what it means. And this is the secret. Even though the collection is terabytes large, you only process 16 gigabytes at a time in batches. And what happens is that when you process a batch, you write back the intermediate results to disk, then you forget about it, go to the second one, maybe you emptied the memory in between, then you write back, then the third one, then you write back. This is how you can work in shards. All right, and then what happens at the end, that's the general way, is that once you have processed the shards one by one, and you have all your partial indices, so the partially computed indices, you merge everything back at the end. In the last step, you merge that back to a single index and back to disk, right? That's the very abstract and high-level way of doing it. Of course, I'm going to go into more details very soon in order to explain how that works, right? And then you have the results. You see the final index is on disk, and that index might be bigger than memory. Can you believe it? I actually built something that might be larger than my memory, and that's okay because again, it's on the disk, right? Okay, do we stop here? Since I don't hear a lot, I think maybe you already had enough to digest, right? Okay, so let me give you the few minutes extra. I'm going to ask you if you understood what I've been telling you, and then we'll take it from there next week. I'm going to explain the more detailed algorithm. BSBI and SPIMI is the name of the two algorithms. And then I'm going to tell you how you can even process data when it doesn't even fit on the disk, when you're actually in the cloud. Right? Okay, so let me just check if you followed. There, and then I will let you go. Of course. There you go. Wonderful. You understood what I've been telling you. Okay. I'm relieved. Very good. Very, very good. Awesome. Okay, so you have a few more minutes. You see you have almost 20 minutes of break before the exercise session. And after that, it's the weekend. So you even get to relax and think about other things than studying. All right, wonderful. So thank you very much, everybody. Thank you for attending the lecture. Thank you, Dan, for moderating the lecture as well. Enjoy your exercise session, enjoy your weekend, and see you next Friday again at 2:15 p.m. Goodbye.